Okay, in the interest of time, we'll just get started right now. So I'm going to begin with a review of some of the material that we discussed yesterday. It's going to be fairly quick, and then we'll move on into the planned agenda for today. So we discussed yesterday that the Brain Image Library is a public resource serving the neuroscience community, providing a persistent repository for microscopy data, and how we at the library rely on contributions from data producers and make it publicly available. Many of the data sets that we receive and bill are quite large, and we provide an extensive analysis ecosystem for both submitters and people interested in exploring other people's data can explore the data in place without downloading it. In terms of existing coverage, the overwhelming amount of data sets contributed to date in the Brain Image Library are from mice, with a handful of data sets from marmosets in humans. In terms of data modalities, most of our primary data sets are slice-wise image stacks from whole brain imaging experiments. In addition, we have thousands of tracings from primary data that is in the archive. In terms of technology, we have data from most microscope types, as well as microscopy related data from spatial transcriptomics and some multimodal experiments as well, such as PatchSeq. In terms of data, we are doubling the number of data sets that we receive about every year. And at the current time, I believe we have over 10 million public files. We also went over the numerous resources that we provide to explore data through our analysis ecosystem. The analysis ecosystem includes small and large memory nodes, nodes with GPUs, as well as our high performance computing systems. We also mentioned our remote desktop environment and its flexibilities and its capabilities to host unique web interfaces to the data, including Open On Demand, which we are going to be using today. We also mentioned the numerous software packages that we support, and we would be more than happy to make other freely available open source software that you need available on our systems so that you can use it and other members of the community can use it as well. We then passed the torch over to Mariah, who went over the differences between a submission and a data set, as well as describing in detail the current metadata schema and how it is used in the various submission models that we have at the Brain Image Library that implement that schema. Luke went over the data submission process, including creating a submission, how to upload data, how to upload metadata, and how to request that the data be validated and made public. Ivan went over LMOD and how it is used to make software installed on our system available for you to use, along with the three important module commands: module avail, which lists all available modules; module load, which you use to load a specific module; and module unload, which allows you to unload that specific module. He also went over Slurm and how to access it from the command line and the important Slurm commands: sinfo, sq, scontrol, and sbatch. Mostly sbatch is what you would use to submit a batch job to the Slurm scheduler, and sq, which will view the information about the jobs available in the Slurm scheduler. He also went over a brief introduction to Open On Demand, which we'll be using for today's exercises, And I did want to make the note that if you are new today and you were not part of the workshop yesterday, don't worry that you missed anything about Open On Demand. Today, Luke will review how to use Open On Demand and particularly how to get to the Jupyter Lab function in Open On Demand. So with that, what we're going to be going over today, there we go. What we're going to be going over next is I'm going to turn the torch over to Mariah, who will go over how one goes about finding existing data in BIL. Then she'll turn it over to Luke, who will give a demonstration of Open On Demand. And if you have any questions, if you weren't part of the workshop yesterday and you're having difficulty, please stop Luke during that presentation and send a note in the chat, and we will get you caught up. Next, we're excited to have Ayana with us today, and she will go over a Jupyter Notebook exercise that involves image registration with some data that's in BIL. Then we're going to have a break, and then Yvonne is going to follow up with some additional exercises for you to perform. And finally, we'll be happy to stick around at 4 o'clock and answer any questions that you may have about BIL, whether it's some content that was gone over yesterday or today, or just even general questions that you may have. And with that, I would like to turn it over to Mariah.
All right, thanks, Alex. Let me just share my screen here. Oh no, can you see my screen? Let me see, let me try that again. All right, is that okay?
Yes.
Perfect. Turn my video on so you can see me, but hi, welcome or welcome back. If you weren't here yesterday, my name is Mariah Kenny. I am the data curator here at the Brain Image Library. And today, during this data exploration workshop, I'm going to be talking about how to find Brain Image Library data. While today, most of what we're going to be going over are tools and all of the great resources that are available to you once you start using Brain Image Library resources. But in order to use these tools, we need to have data, right? So I think it's really important that we go over at the beginning how to access this data, how to find this data, and really understand how data is shared. So we've gone over this a little bit already about what data is in BIL, but I wanted to bring this up and kind of have you thinking about how you would search for data, actually, because these are really a lot of the options that we have within the Brain Image Library of what you can search for, what data is available, and what do you think would be the most beneficial to you in your research. So while we do have mouse, we also have human and marmoset organisms of different types of modalities and experiments. And all of this can be accessed and searched for in multiple different ways in order for you to find what you are looking for, really. So let's get into it. Where can you find BIL data? There are 4 major ways that you can find what you're looking for. One, of course, is if you already know what data sets you're interested in, there is the BIL file system you can go directly to and look at the data and download. There's also the BIL search portal that I'll go over We also, of course, issue DOIs at Bill because one of our goals is making sure that data is easily accessible, and having a DOI is one of the best ways to do that. So we have data set DOIs, we also have group DOIs. And then lastly, because the Brain Image Library is part of the Brain Initiative, there's the BICCN portal, which shows Bill data, but also data from other participating repositories and other data sets that are related to what is in Bill. So let's get started by talking about the Bill file system. This is where your public data is stored. So the data in Bill is organized by submission. If you were at the workshop yesterday, I talked about what a submission was and what a data set is and how those are defined. But the path to the public data utilizes your submission number. So you're able to before you even really submit your data or it's validated in public, you are able to tell where your data will be once it is public. If you understand this little kind of equation here. The path utilizes the submission number. There are unique directories for each data set, which is required whenever you submit your data. The path also includes these subdirectories though. And these subdirectories utilize the first two and then the third and fourth characters of your submission ID. So if we look at this collection number, this example here, we have /bill/data, /bill/data. This is the public portion of the Bill file system. If you were here yesterday, you might remember that we did /bill/LZ, which is your staging area, your landing zone of where you submitted your data. Of course, that is not public, but anything that is under /bill/data is public data. And then you have the / and then AB, which corresponds to the first two characters of your submission ID, then /CD, which are the third and fourth characters. And then you have your submission number, and then your data set subdirectory. So if you wanted to go and you can, let's take a look. If I was on the Bill file system and I wanted to see where this was, I could do that. If you're connected to On Demand, or even if you're on the workshop VM, you'd be able to go and I can see this example works. So I can see this are all the files in this data set. If I wanted to go up a level, I could see all the data sets in that submission. And so with that, let's go back. Because I know this information, I can also figure out what the URL to access this data is going to be. So if I replace this Bill data with the download brainimagelibrary.org, this is the URL to access the data. And if I look at that, you'll also be able to open this in a web browser and download your files directly from any web browser. Same thing, I can go up to the next directory up and see the data sets, or even the sample submission, the entire submission here. So this is really one way that you can share your data set information and have a link to your data set if that is what you can have a link to your data set if you want to share it. I think that this is one way to share it. It's one way you can also, oh, actually, let me talk about one other thing before we move on. There's if you go to, you can also use this if you wanted to create a script to download data set or anything to download directly from this URL using wget or something like that. So let's move on to the search portal. The search portal contains all of the metadata for all the data sets that are public. So if you go to submit.brainimagelibrary.org/search, this thing is the search portal that shows not only all of the links to the data and where that data is stored on disk, which are there, but also includes the metadata, right? The investigator, modality, method, technique, organism, things like that. And you also have the ability to search if you want to search for different organisms or techniques or modalities. And let's go to the search page so I can show you a little bit more about what it does. So if I go to the search portal, if I wanted to look at a specific technique or specific modality, you can filter by that and have all the data that you're looking for there. If I want to look at anatomy or something like that. You can also search for different structures or investigators if you know the grant number, or maybe you even know the collection ID if you're looking for a very specific data set. You already know what you're looking for. I did want to bring your attention to this button though as well, which is download the inventory. So I can download the entire inventory of all public data sets. You might notice that there are less fields here than what the metadata model was that I showed you yesterday. And this is because we did update the metadata model and was implemented this year. So everything here that you're seeing is the previous metadata model. It doesn't include quite as many fields, but you can download and get a full report of exactly what we have available. It tells you the metadata version, projects that it's in, if it's associated with BICCN, submission. There's metadata such as genotype, modality, technique, where it is on disk, and an abstract or a brief description of all of the data. So this is a good place to look if you're really looking to kind of find something new that you might not be aware of. And that's the search portal. Of course, we also have a DOIs as well. There is a DOI portal, which you can see the every single DOI that's issued. Of course, there are two types, the collection and the data set, but you can access this and see every DOI that there is, where it is on disk, or the download link for those data sets as well. You can search for these if you wanted to search cell or any word that's included in the description or the title of the DOI. You can search for that. And there are also DOIs that will have the data set DOI as well. So for each data set that has a DOI, we're in the process of issuing a DOI for every single data set in BIL. This will have more metadata associated with it, but this is a great place to find more metadata for what the data sets that you're interested in. And also, of course, we have grouped data sets that have information for related submissions included in BIL. So the next way that you can find data that's included in BIL is through the BICCN portal. So as I said before, the BICCN is part of the BRAIN initiative and includes BIL data, but also data from these other repositories as well. But you can search for data, and in their inventory. Let's go check it out. So if I were to go here and you can search for, they have different, different keywords, species, modalities, techniques, specimens. So if I wanted to look for something, let's look at connectivity. There's going to be data sets here that are from Bill. There's going to be things as well that aren't from Bill. So it's a good way to find maybe things that are related to the information in Bill as well. But there's a lot there, and it's a good place to find things that are maybe not in Bill, but are relevant to what you're trying to find. Let's see. I did want to bring up the different metadata versions though. So this is the latest metadata version, was implemented at the beginning of the year. This is version 1. This is just a screenshot kind of from the search portal here. And then this is a screenshot of version 2 from one of the DOI pages. And so, of course, this includes much more descriptive metadata. If there's information that you're looking for that isn't there, so maybe you're looking for the sex of one of your specimens, and that might not be included here. That might just be because we haven't, we're in the process of updating all of these to the newest versions wherever possible by going back to investigators and finding more information. So that information might just not be available yet. We hope it will be very soon. But it's good to kind of check to see if you're trying to see if that information is there and it doesn't appear to be there, we just might not have it yet. So with that, please don't hesitate to reach out with any questions. If you ever have a question about a specific data set or how to find something that you're looking for specifically, I'm here to help. And please don't hesitate to reach out. With that, are there any questions? I'd be happy to take them.
Yeah, I have one question, Mariah.
Mhm.
So one of the fields in the metadata and Bill metadata is for R24 repository.
Mhm.
And does it matter what format we put that in? I mean, because initially we get a landing zone, which is converted to the format you showed today. Does it matter what format we put that into that field? Is it automatically converted later?
I will make sure that it is converted later, because with every data set that gets published, I will look at it and make sure that it's right. But you should put the landing zone. That's where it's you're submitting it to, and they will get updated after you submit it.
Simple. Thank you.
No problem. Yes, of course. Any other questions?
Mariah, is the metadata modifiable after submission, or?
Yes, yes and no. So you can modify, so if we're talking about something that already has a DOI, you can modify some of this metadata if you wanted to. After something has a DOI, we can't change maybe like the links to the data that's actually there, right? But if you wanted to add smaller pieces of metadata or make minor changes, yes, we can do that after it's published. If it has a DOI. Before it has a DOI, we have a little bit more leniency there, but once something has a DOI, it really shouldn't be there shouldn't be any major changes made to it.
Yeah, and I do want to add one thing too, and that is if you have a DOI issued and then you have a publication that sort of references that DOI, please send us that publication so we can update the DOI record to reflect that there's a publication that's associated with it.
Yes, yes, absolutely.
Okay, thanks.
No problem. Any other questions? All right. I will hand it over to, I think Luke is going to do a little demonstration on demand.
Sure thing. As long as there's no more questions, I can go hop into this. Okay. So what I'm showing here is the on-demand dashboard for Bill. If you want to get here, in your browser, type in ondemand.bill.psc.edu. And if you go there, you should get prompted for a login. And I just want to make sure everybody can get logged in first and foremost before we continue.
Yes, and I do want to just kind of clarify that. So please follow along with Luke, and you'll be set up for Ayana whenever she takes over after Luke. So please follow along with Luke and do the exercise. Go ahead, Luke.
Sure. So as long as everybody's good and we're logged in, I want to show firstly the job composer we have on the on-demand dashboard. This is where you can create new jobs and run them on Bill hardware. You can do this on the system as well, but it's a little bit easier to do on demand. So I'm going to give an example here with just a default template that you are given. So if you go up to new job, default template, it'll load up a simple hello world script. And when you want to submit the job, just highlight the job you've created and then go up top here and hit submit. So now it's currently running. So we'll have to wait a moment or two for that to finish running. Sometimes you just need to refresh your page to get the status to change, but let's see, that should be a pretty quick job to run. Looks like it completed. And then if you go to the right side here under the folder contents, this will have an out file. And if you click this, it will show the output from that file that's on Bill. So you can do any of your job work through here the same way you could on the file system. Was everybody successful with running that test job? If anybody needs me to repeat anything, I can do that as well.
Yeah, for some reason, it's taking a while to load just the main page. I don't know if
Okay.
anyone else is having that issue. Just not loading. It worked yesterday.
Sure thing. Let me see if I can go back there and, well, regardless, I can show that. I'll show that again anyway.
Oh, yeah, please. Yeah. Sounds good.
So on the on-demand screen, I'm going over to Job Composer. And then I'm going to add a new job here by clicking this drop-down menu, choosing from default template. So that created my new job, which is again that simple Hello World script. You can open the editor down here too to change things, if you please. So if I wanted to also echo workshop, do that as well.
Luke, we have a request for you to slow down.
Sure. Sorry. So again, I'm on the job composer from that on-demand front
So
page.
can you go back and show them
Sure.
that again?
So on the dashboard, it's this third option in here, Job Composer. If we click that, is when we get sent over to the jobs. To create,
Look, could you stop 1 second?
sure.
So if this is the first time you're accessing the Job Composer, the tutorial will turn on. So your screen might get gray, and it will kind of show you a tutorial where you have to keep on clicking next until you get the first, until you can use the window. So apparently, one user was saying that, it's getting a pop-up window. And that's because the tutorial gets turned on the first time they access the Job Composer. So if that happened to you, just keep on clicking next until the window becomes white, and then you can follow the instructions from Luke. So look, if maybe you can restart, because I guess some people are going to are going through the tutorial.
Sure,
Yeah,
apologies
yeah.
for that. I didn't
Which
know
is
that
gonna-
that was up there.
Yeah, yeah. Also, it just took a really long time to load. Just kind of bad luck, but it's loading faster for me now too.
Is anybody else having issues with it loading? If we're all good, I can.
Okay, if
share that.
everyone's good, yeah, Luke, if you can start from the beginning there and just go
Sure.
through the Job Composer again.
Sure. So on the Job Composer, to create a new job, we'll go over to this drop down here, where you have options for from default template, from specified path, or from selected job. I'm just going to use the from default template. So that'll create this new job here. And on the right side of your screen, you can see where the script is located, the name of your script, and the contents of the script. Here being the default template automatically just gives you a hello world script. And like I said, you can edit this script as you please if you go down to the open editor. And this is where you can edit that file. Just getting pop-ups still before it's playing.
So Yvonne, can you go into a breakout room with George and work out the issues?
Okay. If we've all gotten that far, then I'll continue here. So like I showed before, if you want to submit your job, just highlight the job there and then click the submit job button up top. And that'll change the status from not submitted to running.
What? How do we get out of the editor if we edit the text? I didn't see you do that.
To get out of the editor,
Yeah, yeah. I don't see how. To...
you should be able to, up top here, it'll say save.
Yeah,
if you make a change.
I click save, and then
And this, it opens a new tab for you. So it's just
Oh,
go back to
oh.
the other tab.
duh. Okay, thank you.
No problem.
Now I see. Now I see.
And since that job completed, we can go over and see the output file here. You can also view all of this on the VM if you're logged in. But our output file just gives us this hello world. So, like I said, that can operate with any job you want to do. So I'm going to go back over to the Open On Demand main dashboard here and show you all how to start up an instance of Jupyter Lab. So if we go over to the first option here, Jupyter Lab, which is what we'll be doing the next portion of the workshop in, it will ask for the number of hours and the number of nodes and then extra arguments. So for the number of hours, we're going to set that to 8 hours. And then for the extra arguments, give me one moment, I have it copied over on the other side of my screen here. We'll do -n space 8 space -- MEM equals 32 capital G. Just want to leave that up for everyone to see and get that correct. So once you set those arguments there, you can check on or off if you'd like to receive emails when the session begins. I'm just going to leave that off for now. And then go down to launch and click launch. So this is currently queued and it will begin building the session. We'll have to wait a few moments here for it to fully start up and give us an option to launch. Did anybody have any issues with creating that, with that session, creating it? If not, we'll open it up here. I just got my connect to Jupyter button. So I'm going to click that, and well, I imagine some folks are still waiting for that button to pop up, so I'll wait a moment here.
Yeah, so if you get to the point where Luke is right now, if you can give a thumbs up, that would be helpful. If you're having difficulty, feel free to unmute and let us know what your issue is.
Okay, so I saw some thumbs up there, so I think should be good to continue moving on here. So on the Jupyter Lab launcher screen, we have a bunch of options here. The option we're going to be working with is the terminal. So if we click the terminal, you should be given a terminal. And we are going to copy over the files that you'll be working with in the next part of the session. Give me one moment, I can get that command there set up for everybody. And I'll post it in the chat too, so it's easier for people to copy and paste. So we'll do this command here. It's just copying over the notebook files from the workshop data. As I can see, I have this notebooks file, this notebooks directory now. And I'm going to put that in the chat here and leave that up here for folks to copy. If you get things copied over, if you can give a thumbs up, that would be great as well. And if anybody's stuck or has any questions, please feel free to let us know. So with that portion there set up, I did want to mention before I pass it over to Yana, we currently have Jupyter available on the on-demand. We do plan on adding other things in the future. And if there are things that folks are interested in having on-demand, please let us know, because we are open ears and always available to add new hardware or new software for folks to use. So I'm going to pass this over to Yana now if there's any last questions. Emily, I
So-
can jump in a breakout room with you and catch you up.
Thank you.
Hi, everyone. Can you hear me?
I can barely hear you, Yana.
Okay, let me try again. Is it better?
Say something again.
Is it better?
Yes, it's better. It's not perfect, but it's better.
Okay. I can start. Please make me a co-host so that I can share the screen.
Oh, sure thing. You should be good now.
Okay, thank you so much. Can you see my screen now?
Yes.
So I'm in my Open On Demand session in the Jupyter Lab, and I connect to Jupyter. Let me first introduce myself. My name is Jana. I'm a postdoc at the University of Pittsburgh at the Center for Biologic Imaging, and I'm working on developing pipelines for analyzing multi-terabyte images. So I hope everybody has this folder with the notebooks copied to your home directory. I'll go over to this folder. And the notebooks that we will be using today are called downsampling fMost and alignment fMost. Please note that we will not be running the downsampling fMost notebook because it takes a long time to run. fMost datasets are quite common in build. There are a lot of them, and they are 15 to 20 terabytes each. And to register them, we need first to downsample them so that they can fit in the memory. Image registration is specifically useful if you want to compare different experiments in one common coordinates space. If you want to localize robustly a specific region of interest in the brain. I'm sorry. Can you still hear me?
Yes.
Okay, thank you so much. Yeah, so we will be registering the fMost dataset to the Allen Mouse Brain Atlas, the adult mouse, which has 2011 coronal slices. So you can see it at the Allen Institute website at atlas.brainmap.org. So we will be registering the multi-terabyte fMost dataset to the 25 micron voxel spacing atlas here. We chose the fMost dataset because recently we hosted the hackathon for brain registration at Bill. It was in April. The challenge for the hackathon was to register the fMost dataset to the atlas. And I will be talking about the package that successfully did the job. And the package is called BrainReg. This package is very easy to use. That's why it's a good starting point for brain registration. It has very, very nice extensive documentation and an amazing tutorial that will guide you through all the steps. Okay, so let's open first the notebook that does downsampling. We will not run it. I'll just go over through it. But first, let me make sure everybody knows how to work with the Jupyter notebooks. Basically, Jupyter notebooks are Python scripts that are split into the individual small cells. Each cell is meaningful by itself. It can have either one line of code or multiple lines of code function, and usually produce some output. So for example, an image or just some parameters that you want to print. And also you can split the cells with the comments describing what the cells are doing. So it's a really nice way to share your code and to communicate with other people in the community. So for example, let me create a new cell. I can do it either by pressing this plus sign, or just when I'm out of the editing mode, I can press B and create the cell below the current cell, or I can press A to create cell above the current cell. I can delete the cell by pressing double D. I'm pressing D key 2 times, so I'm deleting the cell. You have a lot of useful icons here that allow you to save notebook, add cell, cut cell, copy cell, paste cell. And then also there is this menu here that allows you to either run all cells at once or run, for example, all cells above the current cell that is highlighted, or run the cells below it. And also very importantly, it can export the notebook as Python script or as HTML or as PDF or whatever you like. So basically you can work on something and then just export it as a Python script and run it on build from the command line. So what can I do within the cell? I can, for example, print hello world by convention. And then just to run it, I press either Shift Enter or Control Enter, whichever you like better. Shift Enter takes you to the next cell. So this cell is of type code, as you can see here. There is also type Markdown. So if I change it to Markdown and then I press Shift Enter again, it's just a comment. Also, it can be of the type raw. And raw is just if you want to embed some HTML tags so that then you can export it with and be converted to other formats. So this is a very powerful way for sharing your work. Let me just-
Yana, can
Yeah.
I ask you something?
Sure.
It's all great, but could you make the font a little bit larger?
I'm trying, yeah. Can you see it
There you
better now?
Yes,
Just let me,
thank you so much.
okay. So let me quickly go through this downsampling notebook. Just imagine we have a multi-terabyte data set. It's composed of 11,000, more than that, individual TIFF files, which are stored together in the folder on build that you can find using the way that Mariah showed before. There are many FMOST data sets. You just go to the search page and select the technique FMOST, and you will have a bunch of data set that you can play with later. So this example data set that I'm using is located at this address at build file system. So for alignment purposes, I will be using channel 2, red channel. It just doesn't have as much signal so that it will not distort the alignment. Also, the data set has the JSON file that explains what's in there. We can actually try to print its contents. So we can do, if we start the command in the Jupyter notebook with the exclamation mark, it will be a terminal command. So I can do cat, and then I have this path and this name of the JSON. Just remove the quotation. Yeah, so this is the JSON that describes this data set. And we can see that it's imaged in the coronal plane. So every single TIFF file is one coronal slice of the brain, and there are 11,000 of them. And the resolution which every slice is imaged is 0.35 micron by 0.35 micron. And they are spaced in the axial direction by 1 micron. I also have image shape. That will be interesting for us. Oh my God, something pops up all the time, sorry. Okay, so first we want to downsample each individual file of these 11,000 files, because we cannot do downsampling in memory. It's just too big even for the build resources. It's 15 to 20 terabytes. So we downsample every individual file to 25 microns, because our atlas that we will be registering is 25 micron voxel spacing. We could leave a better resolution, but it will slow down the demonstration. So for the sake of time, we're downsampling to the 25 microns. So we can first get the shape of this brain in microns, so in the physical units, and then we can get the output shape after the downsampling at 25 micron spacing. And this function basically just does this downsampling of individual images. I've created the sequential version of downsampling for you and the parallel version of downsampling using Dask package. So if you've never done parallel computing before, this would be a good example for you how to transform the normal for loop, which will take forever, to something which takes potentially faster. But still, it takes from a few hours to a few days to downsample this huge data set, depending on what resources you have. But the new generation file formats are addressing this problem, and we're trying to switch to them. So after we've resized all these individual files in the lateral dimension, we will also resize in the axial dimension. So we will put all the files together in memory. Now we can do it finally. And also we will read them in parallel through Dask and then downsample them in the remaining third axial direction. And the result we will save. Here I show that you're saving it to your home directory, but I also saved it to a shared folder so we can work with it in the next notebook that will be our exercise for today. So if we look at our data set, so this is one coronal section, one downsampled version of one of 11,000 files. This is a sagittal section and the horizontal section. It is very important to know the orientation at which your brain was imaged, basically to know the origin of the data, which parts of the brain is it the closest to. So how we can do it if the metadata doesn't have it? The new metadata model should already contain orientation, but the old metadata version doesn't. So we have to do it by ourselves. So we see that the first dimension in our array, if you will, is the coronal slice, which goes from the anterior to posterior. And so if I put the 0 here, I will be at the anterior. So the first letter in my 3-letter orientation is anterior. I will mark it here. So anterior. The second letter, to get the second letter, we plot the second dimension, and we see that it's a sagittal section, and it goes from right most edge of the brain to the leftmost edge of the brain. So if we put 0 here, we are at the right edge of the brain. So the second letter is R. And the last letter, we are doing horizontal section in the last dimension, and the very first slice will be at the top of the brain, so it's the superior. So the last letter is S, and we got ARS. Orientation of the atlas is ASR. So to check that we got the orientation correctly, we use the function that maps the stack from one orientation to the other and check if we get what we expect. And we expect to get the same orientation the atlas has. So again, to manage the package that I'm using, the BrainReg, once you install it on your system, well, Ivan already installed it for all of us system-wide, but if you do it locally, when you install it, there are also many useful packages which depend on it, which are installed together with it. For example, the Atlas API, which can not only give you the adult mouse brain atlas, but also the human brain atlas, the zebrafish brain atlas, and red brain atlas, and so on, even developing mouse brain atlas. So whichever works best for you. Even the BrainReg will not only work with FMOS data sets, it also works well on our confocal data, for example, and the light sheet data. There is even the light sheet fluorescence microscopy atlas as well, compatible with this package. So feel free to try it out, it's very powerful. Okay, now we can go to actual exercise. I'll open the alignment FMOS notebook, and we will run cells one by one. We don't actually need to install -- user BrainReg because Ivan already did it for us. But what we would like to do is to save some time and run this command, which creates a symbolic link to the atlas. Normally, BrainReg would download the atlas for us, but just to save time, we already have downloaded it to the build file system, and we just link it to it. Then we import all the packages. Please let me know if something is wrong, if you have questions. Okay. So first,
You just, oh, sorry, Jana, you're hitting Shift Enter to run those? Is that right?
yeah, either
Or
Shift
install?
Enter or Control Enter. So Shift Enter switches you to the next cell, Control Enter leaves you in place. Or you can also run this triangle, but it's easier to use the shortcut. Sure.
Sounds good, thank you.
So we imported all the libraries that we need. We also set up the parameters for plotting. We will save the intermediate data and the outputs to your home directory. So we can do it by specifying the home variable. For me, it's /bill users noisy sky.
I have a module not found error when I try to run the import.
Which module is not found?
BG_Atlas API.
Okay, so then just try running this. You can uncomment it by pressing, by removing the pound character, and then just press Control Enter on it, and it will install BrainReg, but it will take a little bit of time for you. Sorry. Anyway, you can just after you're done with the installation, you can do run all cells so that you can catch up. So you are not obliged to run the cells one by one like I am doing.
Okay.
So now we will open our atlas create an atlas variable. It also takes a little while, but for you it should be fast because we created the links that already downloaded. This is just a helper function for the plots that stretches the contrast. Now, as we can see, our data set has some artifacts in it. It has stripes, just the way it was imaged creates this artifact. And also, it has some background artifact. I will show you it in a while. So now we open the image that we saved from the downsampling notebook. Well, it will be in your home directory, but also I copied it in the shared folder here. Data submissions, July FMOST example 25 microns. So you can just safely run this cell. And now we have our stack. We can check that the shape of it is much, much smaller than we had before. There is no 11,000 layers in any dimension. Now we can explore what it looks like. And yeah, it has artifacts in it. It's the stripes. We can reorient it to the atlas orientation so that every time we run the pre-processing, we run it on exactly the same orientation of the stack, because the stripes are in particularly horizontal direction, so we don't need to process this differently. We need to process this consistently every time we do it. So that's what we did. We reoriented the stack. Now the shape of it changed. If we now plot the first dimension, you see that it got reoriented. Now, if we try to see, for example, the horizontal slice or some other slice, let's try. I'll take the slice in the middle of the brain somewhere, for example, 150 in this case. I can look at this shape and check what are the ranges for my values that I put for plotting. Okay, so the horizontal slice, we see that it has the background artifacts that also can interfere with the alignment process. So we can remove all of these artifacts and the registration will improve because of that. We can still register even without any pre-processing, but the quality will not be as good as after we have removed all the artifacts. So first we remove stripes, and as you notice, the stripes are periodic. These are just the helper functions that we will use. You can get into details later. So what it does, it uses the fast Fourier transforms to identify the counterpart of these stripes in the frequency domain. Because they are periodic, there will be just one specific frequency corresponding to that, which we just need to remove from the data, basically to subtract this frequency. All the image is just a composition of different spatial frequencies. Background has the 0 spatial frequency, and then the finer the detail is, the higher is the spatial frequency. So, for example, if we have a sum of this one 2D slice of our image in the direction of the stripes, so in the vertical direction now, we see that these stripes are periodic. And when we take the fast Fourier transform of this data slice, we see that there is this peak corresponding to our stripes period. This is just some relative spatial frequency of 20, but I gave you here the formula that can actually give you the stripes period in pixels, if you're interested in that. So this is just the image that we had before, and this is what we have after the FFT removal. So if we build the frequency domain representation of our two-dimensional image, we have all the useful information here at the center. And these two small peaks at the distance 20, which we saw before in the 1D plot, are counterparts of our artifact. So we apply the notch filter in this frequency domain to just remove these two dots. There are two kinds of notch filters that I'm using. It's the ideal notch filter and the Gaussian notch filter. Gaussian notch filter takes longer time to run, but it does a better job because it has smooth edges. And the smooth edges reduce the amount of artifacts that are produced by the FFT. So having removed this artifact counterparts, we get this nice image without any stripes. But we still have to deal with this background artifact. That's what we are doing next in the next step at the removal of background. So I defined an iterative function that takes an image and then thresholds it, just binarizes it to see where is the foreground. In our case, it's the brain and the background. And sometimes it fails to do so. And that's why we can iteratively change this threshold to keep within the reasonable number of pixels which are in the foreground and in the background. Usually the background is the foreground is between 20 and like 95% of all the image. That's what we do with each two-dimensional section. We remove the stripes and subtract the background. So this is the mask that we get after this background detection step, the binarization step, basically. And then when we apply this mask to our image, our artifact here on the left, it's just gone. It's not perfect because we have data at the low resolution. If you take the data at slightly higher resolution, for example, with 10 microns, you will have a much better result. But for the sake of speed, we're just sticking to 25 microns. Now, here, I will process the whole three-dimensional stack, one slice at a time. I have the sequential version of pre-processing and the parallel version of the pre-processing. So I will run the parallel version. It will take a little while, but it shouldn't take very long. And then I will save the image that is the result of pre-processing, and we will use it for the registration. Again, if this takes too long, I start basically with the image that I already pre-processed before and just saved in a shared folder. So we will not necessarily need to wait for this to finish. And we can go ahead and basically register our pre-processed image. Now our image is a bit higher quality than we had before, so we are hoping for good registration results. Okay, so I saved the image, the pre-processing completed. You can add some print statement to debug it to see how fast or slow it goes. And now we can finally register our image using BrainReg. BrainReg has a lot of settings, but if you look at its tutorial, the main settings are just few of them. So you have to supply the orientation and the voxel spacing. We know all of that. Well, and input and output also, obviously. So all of the options that you can pass into the BrainReg can be listed by typing BrainReg --help. We could also run BrainReg as a command line tool, either from terminal or from here, from the Jupyter Notebook, like this. BrainReg, then the input, which we have the TIFF stack, the output, the voxel spacing, and the atlas, and the orientation. So atlas, this atlas 25 micron is a default atlas because it's really, really widely used. Also, if you add --debug at the end, you will see the intermediate outputs, which can be useful for you if you are used to Nifty file format. Because BrainReg, under the hood, it uses the NiftyReg medical registration software. So it does the affine transform, followed by the freeform registration. We will see it when we run the actual command. It will give us a very nice, clear logs, what it is doing at each point. So let me just show it to you. Instead of running BrainReg as a command line tool, we just use the Python subprocess module so that we can pass variables into it and reuse our code this way. And also, if you want to include BrainReg into a larger pipeline, this is the way to go with the subprocess, because you can just take outputs of some other scripts and put it into the BrainReg. Okay, let's define this wrapper function that launches the BrainReg and call this function. It will take some time. It can take up to 20 minutes with this 25 micron atlas, but I'm sure it will be much faster than that. And it starts piping the std out which we would see in the terminal normally, it's starting to copy it to the notebook so that we can see the progress. So we are starting registration, loading the image data, then it will be filtering the image data. Then it will be doing the affine registration, followed by freeform registration, and save the deformation fields. Okay, so now it started the affine registration. This step usually is the longest. If you're going to use other atlases, for example, the 10 micron spacing Allen atlas, then it will take longer. It can take 1 hour. So especially this stage is time consuming. I already have this registration run before, and I have the output saved in my home directory. Sorry, yeah, so this is the output, and I can walk you through what we get as an output. We have this NiftyReg directory with the intermediate files. We have the downsampled image. So in this case, we didn't downsample it during the registration, we did it before. But for example, if you would like to get a better pre-processing, you would first downsample to, for example, 10 micron image, and then you will downsample 10 micron during the registration to the 25 micron. It will be handled by BrainReg. So it will be saved to this downsample.tif already in the Atlas orientation. And then you can compare it to the downsampled standard image, which I am showing here. So basically, it is your raw data warped into the Atlas space. So this is how your brain looks in the Atlas space, but at 25 microns in this case. Also, we have the deformation fields. The deformation fields are very important because this is what allows us to go between the coordinate spaces, one way and the other way. Unfortunately, BrainReg saves the deformation fields only from sample image to the atlas, not the back deformation fields. But at the very end of the notebook, I attached the link where I have forked the BrainReg and also saved the deformation fields the other direction. So this is the link to this, if you're interested. So the deformation fields are saved for all the 3 axes in the order in which the axes are specified in the raw data. So deformation field 0 for X, so 1 for Y, 2 for Z. And I will show you in a minute how to use these deformation fields, because this is a very common scenario. I'll see if our registration is complete. Okay, now it's doing the freeform registration. I think it takes a while because we are all doing, hopefully, this at the same time. So it's almost done. After the freeform registration, it will save the deformation field, save this boundary image. The atlas has segmentation, as you probably see. And these boundaries are basically the boundaries between different regions of the brain. So this is the atlas segmentation, how it looks like. This is from the Allen website. Okay, so now it's registering image backwards and generating the inverse transforms. Also, it splits the brain into 2 hemispheres, so it shows where this line separated into hemisphere goes in our raw image. Okay, looks like it's done. Yeah, so it's done in 4 minutes, which is quite good. And this is the fully automated 3D registration. There are also manual tools, which I think are not feasible for the multi-terabyte images. And also there are semi-manual tools and the tools in 2D, but we find the 3D automatic registration tool the most useful. Okay, so now let me show you what's in the output. So I'll run the cells which follow the registration. The transformed image, which is the downsampled standard here, it has the same shape as the atlas, obviously, as we expect. So this is how it looks like. And this is how the boundaries of different regions overlaid to the original data look like. And now, if you are familiar to Napari, if you open this in Napari, you will see basically the number of the region that you are pointing your cursor over. Now let's try to use the deformation fields that we just produced. The common scenario would be to transform some points that are particularly interesting for us. For example, the points of location of some cells that we would like to transform to the atlas space. I'm taking 2 points here. One is somewhere in the cortex and the other is somewhere in the thalamus roughly. So these are my points. I'll just read the image. And these are my points, which I showed you before. So I'm plotting the slice of the raw full resolution data, one of these 11,000 files that we have, because usually when we are looking at the cells or some interesting features, we do that at full resolution. So I'm plotting the full resolution slice. It can take a while. It's a very big image. So maybe I will not rerun this cell. You can do it yourself. Now we define the raw space, the space of raw data, using this BrainGlobe space package, which also gets installed with BrainReg together. So we define the raw space with its orientation, with its shape and resolution, which we all know from the JSON file that I showed you at the beginning. And we define the intermediate downsample space that corresponds exactly to this downsample.tiv file dimensions. So it has the orientation of the atlas, it has the shape of our downsampled image at 25 microns, and it has the resolution of 25, 25, 25 in 3 dimensions. So as we define this space, we can now transform points from the raw space through the downsampled space into the atlas space using these functions taken from the CellFinder package. You can look at it by this link. It's also produced by the same people who created BrainReg. So I make these points an empty array, which is acceptable for the function that I defined above. I downsample them. And so in the downsampled space, this is how they look like. Now we move them through the deformation fields, and the deformation fields are basically a lookup table. So I have the input coordinates, and at these input coordinates, I have the value which corresponds to the output coordinate in millimeters. So we have to scale these deformation fields from millimeters to pixels, which is done here in this function. So we're moving these points through the deformation fields, and this is what we get as a result. At these specific coordinates, we have the specific atlas structures. So these coordinates are now in the atlas space, and they correspond to one specific structure. Maybe this structure has parents, but usually you have the value for the deepest structure, like the child of the child of the child, so not the parent structure. And now if we check which structure our points go in, so the first red point is in primary visual area, and the second green point is in the nucleus of the thalamus, so which we kind of expect. So that's where they were. That's how to work with this BrainReg package. I hope it was useful. Please feel free to ask any questions. And it is a really easy package to start your alignment journey with. And it has very, very nice documentation. So you can go to GitHub page, and here you will have the link to the documentation. Yeah, this is the link to the documentation. And the tutorial will be also here, and you can explore other packages in that bundle. Okay, so that's it. Thank you for your attention. Sorry it took long. Is everybody asleep?
No, thank you. I think that was great.
So does anyone need Yana to go over anything again, anything that people didn't quite get or would benefit from her going over again? Any questions for Yana?
Maybe you could download these notebooks and they will be useful for you in the future, for example, to explore other data sets at Bill.
Yeah. Well, I guess one other question is this, I know that this brain render was presented or used at the hackathon. Are there any other packages that are there others that are available on Bill from the hackathon?
There are many packages out there, but unfortunately, they are not very well documented. For example, there is NSPY, which is based on the ITK. I know Ivan will be talking a little bit about ITK probably. Yeah, so this one is also very popular. There are also packages based on the neural networks that do the alignment, the icon, for example. There is ClearMap. There are many of them, and Allen Institute on their website provides the list of the registration packages used by the community. You can select your programming language. They are written in different programming languages. So there are some for MATLAB. There are lots for Python. There are in C, Java. So there are many packages out there, but most of them are not very well documented, unfortunately. And this was the point of the hackathon, to create a resource that will be reproducible. Now it's still in progress of putting it all together. So.
And I just do want to just mention one other thing. So the hackathon was very successful and we brought people together and they moved in this direction. But we're not there yet. But I do want to let people know that if there's a registration package that you are using and you have some expertise in, that you would like us to make available at Bill to others and document it. We are happy to work with any of you on making that happen. All you need to do is just contact us through Bill support at psc.edu.
Sounds good. It sounds like there are probably packages out there that are good, but as Yana says, not very well documented. So this would be an opportunity to do the documentation to make them more available for other people and make them available on Bill.
Yes. Any additional questions? So the next thing on the agenda is a break. So why don't we take a 15-minute break now? And I guess 15 minutes from now would be about 10 till. So 10 to 3 if you're on the East Coast.
10 to noon out here.
So we'll meet back at 10 till.
Okay, I'm ready to start. Is everyone ready? Hands up or thumbs up if you're ready for me to start. I see 1, 2. And I guess 2 is good enough. Okay, so to do a little recap, this morning, Alex kind of reviewed some of the resources that I talked about yesterday. What I am going to be doing today is 3 guided exercises, or at least 2 guided exercises that will show you how to use some of these resources. Yana's example went in deep to how to use Jupyter Notebooks. I'm going to do another example. One thing that I do want to point out is that because of the resources we have available at Bill, there's some very good Python packages that we can use to do computations in parallel to make some of our computations more efficient. Yana mentioned Dask. Dask is widely used and very popular. I'm going to be showing how to use the multiprocessing package for Python on a very straightforward example. The examples that I'm going to be showing you today are not computationally expensive nor difficult. They're just proof of concepts of how you can use some of the technology that we have available on Bell. Okay, so for starters, if you look at the agenda, if you look at the resources for the first day, you'll notice that in my section for yesterday, there's a link that says to access the Brain Image Library documentation, click here. That is the full documentation on how to use the Bell resources, including some of the talks that Mariah and Luke gave this morning and yesterday. But it also includes the computational or the analysis ecosystem. So I share with you over Slack, and I can share this, I guess, over, can share the same link in Zoom. Give me a second. How do I do this? A link to the document that I will be using right now. I am not going to be using a presentation or a PowerPoint. I'm just going to be using this document. So if you want to follow that document so that you can follow what I'm doing, just a reminder, we are recording these sessions and the sessions will be made available to you. So if you prefer to just follow what I'm doing and then you want to do it at a later time, be my guest. But if you want, you can follow me on the exercises. So if you click on this link, it will take you to this page that you can see on my right that I have here, which is the chapter of the analysis ecosystem. And in here, you will find descriptions from everything on how to use X2Go, which we already done a couple of times today and yesterday, how to SSH, and how to use LMOD, etc., which I am not going to do. But what I am going to do is that if you click here on expand all, you're going to see at the bottom of this table of contents some exercises. So we're going to be doing 3 exercises today. Exercise 0, part of exercise 2, and exercise 6. So I was not planning on doing exercise 0, but since we got 10 more minutes than I allocated, I think I'm gonna do it. This is using the Job Composer, a very simple Hello World example. It is a little bit more thorough than the example that Luke did this morning. And then we're gonna do another example using Job Composer on exercise 2, and then exercise 6. We're going to do some contrast stretching of some images that are on /real/data, and we're going to do that in parallel. And again, the point of these 3 exercises is to highlight the resources that we have available. Okay, so first of all, hands up if you're following me. If you have any questions, raise your hand. If not, I will continue. I can look at the chat. I see everyone, it's okay. Okay, good. Everyone's okay. Okay, so I'm gonna click on exercise 0. By the way, the way that they're presented, these exercises in the documentation, you should be able to follow along, even if you want to do this later. It has screenshots and it's very well documented. So you can do this on your own, but the whole point of the exercise 0 that I'm going to be following with you now is to show you how to use the composer to do a little bit more than just the Hello World example. So the first thing that we're going to do is go again to On Demand, click the Job Composer, and this will open a new page, right? I'm going to assume that somewhere in this list, you have the example that you completed with Luke this morning. And we're going to do sort of a similar example, but using LMOD. Okay, so I'm going to create a new job from template. Okay, just like Luke did this morning, and it will create a new job. And you can see here that it says the status is not submitted because I have not submitted the job. And if I go to the bottom, you're going to notice that it's my Hello World example. Okay, so everyone follows me up until this point? Yes, okay, good. So I'm just gonna click open editor and it's gonna open a new page. Let's see if I can make this a little bit larger. Okay, and in here, if I edit this shell script, that it's the main job. So if you look at my exercise 0, it basically describes all the steps that I have done with you so far, with the exception that it will have here some code that you can copy and that you can paste into the job composer. And that's exactly what I'm going to do. I'm just going to copy, paste, and replace the contents. Again, this is a very simple example, but the whole point of showing you this example is that you can use LMOD to load modules into Job Composer. And in this particular case, I'm loading Anaconda 3. So now I am able to use pip to install a package in my user space. Okay. And for those who are familiar with pip, this just says install it in my home directory. And this means reinstall it again if it's installed. I just put this so that you know, it's a proof of concept, not because you need to reinstall it anytime, every time. And then I will click save. Okay, wait, who's following me? Has everyone been able to follow? Okay, good. I see one. See someone wanting to join. Okay, good. Okay.
Actually, I'm
go kind of.
just looking, sorry to interrupt. I'm just looking for the code to copy. I didn't have your, I know.
Did you go? Yes.
I went-
Did you?
Thank you. I clicked on the link, but for some
You
reason,
click on Slack. It takes you to this page. Oh wait, I'm using. And then when you look at the table of contents, if you click expand all, here I can collapse. Sorry, my bad. So you can click expand all, and it will expand the table of contents. And then at the bottom, at the bottom of the table. Sorry, I don't know what I'm doing that. If you look at the bottom of the table of contents, there are some exercises. Then go to exercise 0. And if you keep scrolling down, eventually you're gonna hit the contents of the script. Where would I? Oh, here. You see it now?
yes, I'm getting there, almost there. Exercise 0. And there we go. Yeah, I got it. Thank you.
Okay, good, no problem. And again, this is a proof of concept. It's a little bit different from Luke was doing this morning. The whole point is to show that you can use LMOD to just load any module that we have available, any command line tool that you can just load it into our script. I'm going to click save. Once you click save, if you go back to the Job Composer, you're going to notice that now the script has been updated, right? And now because it has been updated, you can just, in this case, click run, submit the job, and then it will run. Again, this is a very simple example. It will take like 10 seconds to install the Python package, and then it will run. So this is not a complicated example. We're just trying to show that the tools that we talked about yesterday can be used in the Job Composer. The same shell scripts that work on the hardware, whether you're building them on terminal, connecting to an editor on SSH, or using X2Go, the same shell scripts that work with Slurm on any of those resources will also work in the Job Composer, okay? So that was the whole point of exercise 0. Now, we can let this run. It will take a minute, and then we'll see that the status is completed. I mean, I'm hoping that it will run successfully. So if I refresh the page, it will tell me that it's still running. Okay, so I'll just leave it there. And again, remember, the whole idea of the Job Composer is that we don't have to sit down and wait until it's done. We can just leave it here. We can revisit it in a few minutes, and we can go on to exercise 2. Sorry. So now I'm going to go to exercise 2, which again will use the Job Composer, but it's a little bit more complicated because the simple hello world takes less than a minute, and that's kind of trivial. But in reality, we want to use the job composers when we have more complicated workflows or pipelines that take longer. Again, a lot of people like to use Slurm directly on the shell, but this is another option. So I'm not going to go through all the details of exercise 2 because this is an exercise that we've done on previous workshops. But the main idea is that we explore the portal and we find a data set of interest, which is documented here. It's data set 84C1. And then we would like to explore the images visually. Unfortunately, these images are not contrast stretched, so when we open them, we cannot see any signal. So the quickest thing that we can do is just contrast stretch them and just to see what they're made of. And again, if you follow this example, it will tell you how we can use ImageMagick so we can contrast stretch the image. And in this case, we're doing it and submitted through to Slurm through SVatch. But what we want to do is do exactly the same exercise, but now use the job composer. Okay, so now if you go to the bottom of the exercise, you'll see a section that says do it on Open On Demand. And that's what we're going to do. Oh, by the way, my job completed, the one that I submitted, it should have been completed for all of you. Okay. If that's the case, like Luke said this morning, if you want to see the output of your job, just simply click this Slurm out file. By the way, this number that you see here in the out file name is the job ID on Slurm, the Slurm job ID. If you want to use some other tool to figure out the status of the job. Since this is just a regular text file, by clicking on it, it should open. And there you go. Basically, PyFiglet is an application that just does kind of like pretty print of text, and it worked. It worked. It installed the library and then it ran what I wanted it to run. Again, this is a very trivial example. But now we're going to create a second job, and this second job is a little bit more complicated. Why is it more complicated? Well, it is more complicated because we're going to go through a folder of images. We're going to try to contrast stretch them. But the reality is some of these images are quite large. So we will need more than just the default resources that we get with the job composer. We need to allocate, probably increase the number of cores and increase the amount of memory assigned to that particular job. Fortunately, even though through the job composer, we cannot pass parameters like we can on SVatch, we can add those parameters to the shell script itself so that when submitted through the job composer, Slurm knows what resources to allocate to this job. And that's exactly what we're going to do. I'm just simply going to start a new job, default from template, and just like before, it's going to create my simple hello world. And I'm going to edit this file by clicking the editor. Now, is everyone following me now? Is everyone here at the same step that I am? I see Catherine says okay. I'm hoping other people are following me. Okay, good. So, like I said, I'm going to go to this section in the documentation that says do it on Open On Demand. And I provided the script for you, but I'm going to explain what the script does. So if you go to the do it on Open On Demand, you're going to see the block that corresponds to what I want to do. And I'm going to go through all of the details. Okay. So the first thing that I'm going to do is increase the resources allocated to the script. For those familiar using Slurm, all I'm doing is passing this to, maybe it's just too small. Let me make it larger. I'm passing these input parameters where I'm saying assign 2 cores and increase the amount of memory to 8 gigs. Based on the number of people on this today, we can increase it to even something larger. But reality is, even if I increase the amount of, for example, memory allocated on this particular job, this job is designed to run sequentially. So at any given time, we might not use more than 8 gigs at most. But just for the sake of discussion, I'm increasing it to 16. You can also increase the number of cores to 4. By the way, these resources that I'm allocating on this particular job are different than the resources that were allocated to your session on Jupyter Lab. Okay, so this is a different job. And then what I'm doing is just loading ImageMagick, which contains many binaries. One of them is convert, and I'm just saying convert, contrast stretch these images at 15%. Now the main difference, which I wanted to highlight, is we have a set of SSDs that get mounted on /local for each job. So that means that every time that you request a job, whether it's using Slurm or using Open on Demand, you will create a random folder that gets mapped to /local. And that particular folder that gets created for your job in general has faster performance at writing and reading to that particular folder than it does to writing or reading to your home directory. That's why what this job is doing is saving all of the files to /local, and at the end of my computation, it will copy those files back to my home directory, to my desktop, sorry, on the folder exercise 2, because this is the exercise 2. Does everyone follow me? Yes, no, thumbs down if you don't follow or you have a question. Okay, everyone followed? Okay, good. Very good. What am I doing? I'm confusing screens. Okay, so just like before, now that I updated the script to the way that I want it to be updated, I'm just gonna click save. Boom. And if I go back to my job, my script will get updated. And now if I click run, my job will get submitted. Now, this is no simple job. I am doing this sequentially. These images are kind of large. So in reality, this job will take more than an hour to start and finish. So keep that in mind. We can come back, hopefully by the end of this experience, this will be done and we can export images. So again, using Job Composer, you can use /local. The compute nodes also have scratch space on /scratch. Just know that the scratch space on each of the compute nodes is a shared resource. So we expect you to erase whatever files you have created on /scratch after you finish running your jobs. I think there is a sort of like cron job that erases files that are older than 7 days. So we do not guarantee we do not guarantee that your files on either /scratch or /local will be there if you do not remove them yourself. Okay,
Question, are user permissions set so that, I mean, to like, 700 or are they globally readable, read write of the files written there?
I do not know. Alex, do you know?
Yeah, it should be that what the default is for a typical user, which I believe is you only have access to your files. I'm not sure if by default group gets any access. I think it doesn't.
Okay.
A
Yeah,
quick
for
quick check
/scratch, I
is to
think
really
that's
just do a quick job and just do an ls-l on /local, and it should tell you.
Sounds good.
Well, I think the difference is that /local goes away as soon as your job ends, because it's literally a temporary file that we just map it to /local to make it easy for you when you write your scripts. But /scratch is not. /scratch is shared, and there is a potential that your file will be there, for X number of days or hours after you finish your computation. You cannot erase files from other users. That's why we say that it's a shared space. But I know there is a job that erases them continuously. I just don't know if it's set up to like a week, a few days, a few hours. That I do not know. Again, the difference is that /local
Alex, what is it? It's SSD.
So
they're,
slash local is NVMe SSD that's directly mounted on the node itself. So it's node local storage. Whereas Scratch is an external fast storage.
Okay. Yeah.
So slash local would be faster in the grand scheme of things than slash Scratch, but slash Scratch would hold more.
Oh, I see. Do you know the limitations on slash local?
I believe those are 7 terabyte NVMEs on each of the L nodes.
Okay. Okay. Okay, so we can leave this job running. It's running on the background. Again, like I said before, it's going to take a while for them to run. You can take a look at Slurm out and it will give you an idea what's happening. This binding thing, it's fine. That's not a big deal. That's just because ImageMagick is mounted on a Singularity container, so that's a common warning. Okay, so now, Yana, when you did your exercise, sorry, I was a few minutes late. Did they copy every single notebook, or they just copied your notebook?
They copied all the the whole folder.
Okay, good. So if you copy the whole folder with all of the notebooks, then you can simply go to Bill on Demand. We can go to Jupyter Lab. You might have an interactive session already open. I don't know if I have one though. I do. Okay, I do. Does everyone have a Jupyter Lab instance running? Raise your hand
No.
if you don't.
No, I don't. I closed mine.
Okay, you can open a new one. And then we can wait.
All right.
Are there any parameters that they should use to open up the open on
Um,
demand?
Yes. Let me open a new one then. So I think I told Luke to use these parameters. They're not particularly. I mean, again, this is just kind of like a proof of concept. We're not going to use 32 gigs or 16 cores, but this is more like a proof of concept that you can allocate as much as it's in the node. So in this case, I requested it for 8 hours for one node, and 16 cores and 32 gigs of RAM. Now that being said, remember what I said on the first day. There are no charges to bill. However, on demand is available on Bridges too, but if you use it, this UI has a little bit more options because you will be asked what account to charge and what queue you should be using. In our case, we don't ask what partition should be used because you all use compute, and we don't ask for an account because there are no charges associated with using our resources. Okay, so you can just launch, and I launch a new one, but it doesn't matter, we have enough resources. And once you're done, you can just connect to Jupyter. And then we wait. So raise your hand if everyone is, it's here. Good. Okay. Okay, good. So I'm gonna make this larger because for this particular exercise, we don't need the documentation, though in the documentation, it will explain how to open it. So I'm assuming that everyone copied a folder and you have access to a particular notebook called, I copied them over, didn't I? I'm gonna do the same thing like you did. I didn't copy mine. So I'm gonna open terminal, and in terminal, I'm gonna copy Bill workshop 2022 data submission, July notebooks, and I'm gonna copy the contents of that folder here. Okay, good. So now I have my notebooks here. I'm gonna refresh, and I should see them now. And one of the notebooks that I download, I should be called exercise 6. Can everyone find the exercise 6 contrast stretch image? Let's see, I see 2 messages. I am going to have, okay. Okay. I'm just gonna open it. There we go. And now I have my open, give it a second. And now I have my open Jupyter notebook. Is everyone here? Yes? Hands up if you're following me. Okay, I see 2. Okay, fair enough. So what we're gonna do, this is a very simple exercise. Like I said before, we're gonna be able to open an image where there's a data set of interest. We want to explore it visually. So what I'm going to do is I'm gonna use OpenCV to contrast stretch. Before I used ImageMagick, it was easy to do it in Bash. It's, you know, the binaries are very straightforward, but in this case that I'm doing it Pythonically, I prefer to use some of the resource. So OpenCV does the trick. It's very straightforward. So what I did, and it seems like a little bit of an overkill, is that I created a function. And what this function does is that it takes a file, a TIFF file in this case, and then it contrast stretched it, and then it saves it to disk. But I created a function for this. And my main reasoning for creating a function is because I am going to be creating a pool using the multiprocessing toolbox, and then I'm gonna run this in parallel. In this particular case, even though I allocated 16 cores, like you saw when I requested the resources on Jupyter, I'm going to keep it safe, and I'm going to set my number of threads to 8. Okay, so if we look at this exercise, we're loading the necessary toolboxes. Then we're creating this sort of like dummy function that does what I wanted to do. It takes an input file as a string, and then it saves it to local. And then I'm going to create a pool that will have 8 threads using the multiprocessing toolbox. And then I'm going to be doing something very straightforward. I'm going to be using the pathlib library to find all the files in that particular folder associated with a collection of interest. And then I'm going to send that list to the pool. And then if everything works out correctly, then I will be able to contrast stretch 8 images at a time, increasing. What module are you not being able to load? Ed, I saw your message. Which one are you not unable to load?
NatSort.
NatSort. Oh, so if you cannot, okay. So if you are unable, I'm gonna do it here. So I'm gonna add. If you're unable to, you can do from the same notebook. You can do pip install user NatSort. I apologize for that. I thought I had it installed. And then if you run that cell, in my case, it should say that it's already installed, but in your case, it should install it. Right? Like in my case, it's saying that it's already satisfied. And then I'm going to run the second cell. We will only import the packages. Then I'm going to run this one. It will define the function. And hopefully, by the way, keep in mind that what we're doing here, it's very similar to what we were doing in the ImageMagick example in exercise 2. But keep in mind that I told you that using ImageMagick sequentially will take over an hour to run. I'm hoping that this using OpenCV, which has been optimized, and using the multiprocessing toolbox, package should be faster. So I'm just going to click that and hope for the best. Oh, and you can see that it's pretty straightforward. It's doing it very quickly. Actually, very, very quickly. Those are good news. And we're gonna wait for a few minutes. And again, keep in mind that this is the whole point of this exercise, that there are multiple ways that we can perform one task, even when the resources that we have available are the same. But just by using a different tool, we might get a significant increase in performance. Just like the previous file, we're writing to /local, it should be faster. Now there's gonna be a little trick here. You can see that I'm writing PNG files, but when I copy these files here on my next command, you might see some TIFF files. And that's because my job composer and my notebook are using the same space as /local. But that's fine, that's not a big deal. So now, I don't think it's done, is it done? Oh yeah, it's done, it finished in just like 2 minutes. And I'm gonna copy over the files. And now you're gonna see that in my desktop, I have a folder called exercise 6 with all the images that I created. I'm gonna remove these PNG files from /local. I don't want any conflict. Let's just see if we can explore at least one image. And we can, hopefully. Let's see. So now we're going to be using the Matplotlib widget, which allows us a little bit of an exploration of the image. Not a lot, but at least just a little bit better than just open it. Let's see, there we go. Keep in mind, I did contrast stretch, but I did not downsample. So this image is kind of like large. And this is it. This is the example of an image that I could not explore before, and now because I contrast stretch it, I can. The widget allows for a little bit of an exploration. So if you click this square box, you can zoom in. And it takes a little while because it's downloading the image every time you try to zoom in. So be patient. But in a nutshell, using this Jupyter notebook and using a different tool and doing it in parallel, we were able to do the same computation that we did sequentially. Instead of 1 hour, we got it running in less than 2 or 3 minutes. So that's pretty impressive from my perspective. Then another thing that I wanted to mention, if you look at Yana's notebook this morning, you know, she was mentioning that the downsampling of the whole data set could be measured in days. You could create a notebook that, you know, that does that, and then you can submit your notebook itself on Shell as well. So you can do some exploration using the Jupyter notebook, and then you can submit it using the job manager, the job composer. You don't have to use JupyterLab to submit the notebook itself, but that's kind of like an advanced topic for another day. Does anybody have any questions so far? No? Okay, so let me do kind of like a little bit review because some people had some questions today. So there are multiple ways that you can connect to our resources. You don't have to use them all at the same time. X2Go is a remote desktop connection that you can use to explore data or use the resource available at the workshop VM. The workshop VM is a large resource, so you're sharing it with other users. You can use it for computation, but you cannot slice the resources efficiently. So basically, it's kind of like all of you are connecting to the same machine and are competing for resources. Then you can SSH as well to the workshop VM or any of the VMs that were listed yesterday, including the login VM. But through any of them, you can connect to the L nodes or the large memory nodes that we provide 8 of them. You cannot connect directly to the large memory nodes using X2Go. You can only submit jobs using Slurm, which is the job scheduler. You can use Open On Demand, which is a different resource that is accessible through a browser to use the L nodes, either to compose the job using the job composer, which is similar to writing a shell script for Slurm on terminal, or you can use JupyterLab or Jupyter Notebook to start an instance that you can run notebooks in. In the near future, we're going to be installing and deploying RStudio, which is a commonly used tool in on-demand, and we are open to exploring other tools that you might find useful use in and on demand. But basically, they're all connected to the same resources. Your home directory is the same, independently of where you log in into the resources. It's always on /build/users. So whether you're connecting an on-demand or shell or X2Go, it's the same files. And know that at every compute node you have /local and /scratch as some temporary locations for you to write files. And your home directory, anything you write to your home directory should be accessible through any resource. The same thing applies for /build/data, which is our public data. Also know that our public data is mounted on both Bridges 2 and NeoCortex, which are other resources available at PSC. However, to use those resources, you need to request an allocation, and that's a different process. And keep in mind that if you request access to Bridges 2 or NeoCortex, there is a charge, an allocation that gets consumed as you run JAWS, which we do not have the same charges here on Bill. The resources are available to all of you without any cost or charge. And I think that's about it. Does anybody have any other questions? Suggestions?
Well, I know this wasn't the main point, but if we had tried to open the images before we ran the CB2 portion of the script, then they would have just been basically black, right? Yeah. Okay.
Yeah. Basically, yeah.
Uh-huh.
Yeah.
Cool.
And again, just contour stretching is just for the whole. I mean, yeah, just for data, for visualization and exploration. That's the bottom line. Yeah. And does anybody got any questions? Well, I guess Alex will end up the session today. But if you have any questions regarding the computational resources, or if there are any other libraries or software that you wanted deployed on Build, just send an email to Build support, and we'll do our best to get it deployed as soon as possible. Thank you.
Yes, thank you. And I just want to just a few comments before we wrap up. Just wanted to mention, by all means, use the bill-support@psc.edu email address for any questions that you may have about Bill, whether they're metadata related, whether it's installing software, whether it's making your data publicly available. Use that email address for any inquiries that you have for Bill. The other thing to note is that we will be sending out a survey about these workshops. And this is the first time that we've expanded our original data submission workshop into 2 days and highlighted open on demand. So we look forward to your feedback on the new additions, as well as suggestions for materials that we can include in future workshops of this type.